It's now time to investigate a couple of core fundamental, if that's not redundant, ideas in rotational motion, and that is the rotational kinetic energy and the moment of inertia. So let's start with a generalized body, and this body is going to have an infinite number of point masses that make it up. So we'll consider three of them, M1, M2, and M3, and they each have their respective vector positions from point P. So point P is just chosen arbitrarily here, and every point on this object has some position vector associated with it. So these are the representations of that, and each one of these has its characteristic velocity. Notice that the velocity, if the system is rotating, which it is related to the radius from point P, and the further away it is, the faster it's going, for obvious reasons. V is equal to r omega. That is the reason why. So the kinetic energy of the ith particle is 1/2 MIVI squared. So the kinetic energy of the total rotating body is just the sum of all of those. And so we express it as such. However, the velocity, or we'll just call it speed, is r omega. So where we see this vi squared, we'll put in r squared omega squared. So that's our new kinetic energy. So kinetic energy is sum of the 1/2 mi ri squareds omega I squareds. All right. But also, all omegas are, you guessed it, equal because of the reasons we talked about. It's a rigid body, and so the angular velocity is the same for all particles. Therefore, we can factor out the 1/2 mi ri squareds and multiply everything by just omega squared. It's the same omega. So here it is written a little more succinctly. And now this quantity, summation of mi ri squareds, has a special name, and it's called yes, the moment of inertia. So that is going to be something that's very important in our subsequent problem solving. So we are introducing that now. The symbol is I. And we also recognize then that the kinetic energy from what we just discussed is 1/2 I omega squared. Let's compare for a moment rotational and translational kinetic energy. So rotational, we just learned, is 1/2 I omega squared. And of course translational is 1/2 mv squared. So you see a correlation in how they look. We have a couple of terms that have been interchanged here. So rotation is related to I and omega, moment of inertia and angular velocity. Correspondingly, translational kinetic energy is related to mass and velocity, or speed. So I, moment of inertia, and m, mass, are related across these two ways of thinking about the energy, and omega and v as well. So those are the correlations between rotation and translation. Let's do a calculation of the moment of inertia for a collection of point masses. We'll just do 3. So here's 3 point masses, M1, M2, M3, and they are connected somehow to a thin rod, and it's rotating as shown. So they're all on the same plane, if that's not clear. So these masses are on the same plane, and they're perpendicular to the rod. At this point is the particular position vectors. They're all perpendicular to the rod. So they all lie in the same plane. All right. So we just, to get the moment of inertia, we add the individual moments of inertia for each particle. M1 R1 squared plus M2 R2 squared plus M3 R3 squared. So there it is. Now that has a particular value, and if we rotate those same set of masses about a different axis of rotation, then we're going to get a different moment of inertia because the particular radii will change. So what I'm going to do is try and show that. I'm going to take this rod and basically just rotate it so that it's in this orientation. And think of these three masses still in their same spatial position you see them now. So here they are, same spatial position. But because we've rotated the rod 90 degrees, the radii are going to be different to the three masses. So here they are, R1, R2, R3. So if that didn't make a lot of sense, don't worry about it because it doesn't matter. The point is, around a different axis of rotation, the radii are going to change. And if the radii changes, then of course the moment of inertia will change as well for that system of particles. So we'll be using that in maybe easier to understand examples going forward. So now let's dig a little deeper into rotational moment of inertia theory and see what we can discover. So we have that the moment of inertia is the sum of all the MIRI squareds. For a uniformly shaped object, here's what you want to do. So you can divide the object into an infinite number of infinitesimal masses, each with delta m or dm, differential mass, its own unique distance r from the axis of rotation. So then what are we going to do? Then the moment of inertia is the integral of the r squared dm. So notice that this has the same form of our summation. Obviously the integral is like the summation. There's the r squared, and the little mi is the dm. So this is the general form for discovering the moment of inertia. Now use the density to relate the mass and volume of each of these little dm's, every little element, to the mass and volume of the object as a whole. So density is rho. That's right, it's not momentum. Tough, just deal with it. So momentum is mass over volume, and mass over volume as the whole is also equal to the ratio of the differentials of those two physical quantities. So that's dm over dv. So if mass over volume is density, so is differential mass over differential volume. This will be useful because look at this dm. We have dm here. We're not going to be able to integrate directly with dm. But dm is equal to rho dv. Multiply both sides by dv. And as we'll see, that will set us in the right direction to actually solve the problems for the moment of inertia of a particular object. Let's do it. Let's use this idea to discover the moment of inertia for a thin rod pivoted about a particular point on the rod, some distance h from one end. So there is h. The whole rod is of length L. So the remainder is L minus h on this side. Cross-sectional area A, mass M total. The volume of this rod is simply the cross-sectional area times the length. All right, so the moment of inertia then is integral of x squared dm. Well, it's not immediately obvious what to do there because we got this dm. How are we going to integrate the dm's? So let's look at how we can break this up into its little tiny dx's. So x is in this direction. These are the differential mass elements and also the differential length, or dx, along the rod. So the moment of inertia of the ith differential element, or small element, delta m xi squared. The problem is that we need dm in terms of dx so we can integrate the length of the rod. We can't do it directly with respect to dm. So as we just learned, we can consider the density, mass over volume, which is dm dv, dm over dv. Thus, we can express dm as rho dv. But dv, or v itself, is cross-sectional area times length. So we can utilize that and call it rho dv is rho a dx. So now we have transposed, so to speak, dm into dx. The moment of inertia then is integral of x squared dm, where dm is this rho a dx. Very wonderful. So that is x squared rho. Now, al over L. Looks like we're going the wrong direction here in terms of simplification. However, what's al? Al is volume. And the reason I'm expressing it in this way is because rho v, density times volume, is mass. So we're going to express this now in terms of mass. So integral of x squared m over L. The mass is a fundamental characteristic of the rod itself and easy to determine. So now we have m over L coming outside because it's a constant, x squared dx, from negative h to L minus h. And so we do the math on this, and we get x to the third over 3 times m over L from those limits. And so let's plug it all in, and we get this. Now, since it's L minus h to the third power, that's going to be a little bit cumbersome. So let me do that for you. Here it is. And this expands to this expression, which then becomes this. And those h's go away, the h to the thirds at least. So this reduces to L to the third minus 3L squared h plus 3LH squared. Now we can cancel out one of those L's with this L, so that'll simplify it a little bit. And we have that the moment of inertia is m over 3 times the quantity of L squared minus 3LH plus 3H squared. So that's the general formula, the way we set this up for the moment of inertia, of length L, mass m, and distance h from one end from which we are rotating that uniform density thin rod. So let's look at some special cases now that will simplify this expression quite a bit. So just repeating the information for the rod here. And now we're going to consider two cases. First of all, if h is equal to 0. Well, if h is equal to 0, of course, this term and this term just go away. So I is equal to m over 3 L squared. Very wonderful. And we have it pivoted about the end. Now that's really a fairly common situation in practical circumstances, pivoting a rod at one end. So it rotates about the end, and the moment of inertia then is 1/3 mL squared. And of course that's highlighted in blue, meaning it's pretty important. It's a very, very common object whose moment of inertia you should be somewhat familiar with. Let's now rotate it in the center. H is equal to L over 2. So that'll change things a little bit. Rotating about the middle, if we put L over 2 in for H in the general formula, we have m over 3 times L squared minus 3L squared over 2 plus 3L squared over 4. So then L squared can factor out of this, and we have 1 minus 3s plus 3/4, which is, let's see, 4/4 minus 6/4 is minus 2/4 plus 3/4 is 1/4. So ml squared over 3 times 1/4 gives us 1/12 ml squared. So just by rotating the same rod about its center instead of about the end, we've decreased the moment of inertia by a factor of 4, which is quite significant.